Intersection is a word that we're likely familiar with from many other contexts. In math specifically, we might discuss the intersection of two lines being the point where they meet, or perhaps if they're parallel, we recognize this specifically when two lines do not intersect. But even outside of math, we use this word all of the time to describe the places where things overlap, roads being a common example. We drive through a four-way intersection when two roads cross each other. Thinking of intersections as the place where things overlap is a great intuition to carry into our study for set theory, as we'll define the operation of intersecting two sets as their overlap. It also works well to help us visualize the operation. As discussed in the previous video, we can use Venn diagrams to visualize sets. If we draw a Venn diagram for two sets A and B, their intersection is the region where they overlap. More specifically, the intersection of sets A and B, wherein A intersect B, is the set of elements common to both A and B. This intersection symbol, which looks kind of like an upside down U, is similar to a plus minus or product symbol in the sense that it tells us to operate on the two sets it sits between. Specifically telling us here that A intersect B is the set of elements X such that X is an element of A and X is an element of B. Now, I want to emphasize the and here because when you think intersection, you can think and. This will be a useful association when studying logic as well, but for now, an element belongs to the intersection of A and B if it belongs to both A and B. Let's consider an example. Say set A was equal to the set 1, 2, 3, 4, and set B was equal to 2, 4, 6, 8. We can find the intersection of A and B by identifying the elements that are common between both sets. In other words, the elements that belong to both A and B, where they overlap. Looking at each element, one belongs only to set A, so it does not belong to our intersection. 2 belongs to A and B, so it does belong to our intersection. Similarly, 3 only belongs to A, 6 only belongs to B, and 8 only belongs to B as well, so none of these would be included in the intersection. 4, though, does belong to both, and so we'll include that. These two sets have two elements in common, 2 and 4. Thus, the intersection of A and B is the set 2, 4. Not all sets overlap, though. We could adjust our Venn diagram, for instance, to look like this. These are known as disjoint sets. Specifically, two sets A and B are disjoint if they share no common elements. So for example, if we let A equal to 1, 3, 5, 7 and B equal to 2, 4, 6, 8, these two sets share nothing in common. They're disjoint. So what happens here if we try to take their intersection? Well, we know A intersect B is all of the elements that A and B have in common. Since they have no elements in common, this would then be the set with no elements, otherwise known as an empty set. So in a case like this, we would write A intersect B is equal to the empty set. As we've seen before with lines, roadways, or Venn diagrams, intersections in general represent the places where things overlap, and this still holds true for set theory. Yes, in set theory, it is an operation, taking two sets and operating on them in some way to yield a single resulting set, in the same way addition, subtraction, or multiplication operate on a pair of numbers, combining them in some way to get a sum, a difference, or a product. But when we think intersection, we really can just rely on this intuition and think about and because it's really just about the elements that are common, the ones that belong to both A and B. Now, we'll be discussing other ways to operate on sets in the upcoming videos, but in the meantime, I hope you found this one helpful. Let me know if you do have any questions in the comments below, and thanks for watching. Have a great rest of your day.